Alan, just when I thought I was beginning to really understand cosmology in the late 1990s, suddenly I wake up and now there's dark energy, which supposedly is 70% of the entire energy density of the universe. And it's driving the universe and all sorts of things. What is dark energy, and how can we begin to understand it and its significance?
Okay. Well, I was just as shocked as you were about dark energy, and I've felt the same way ever since. That with the dark energy, it's very hard to have any real feeling that we really understand ultimately what the universe is doing. It's a very peculiar situation because we have theoretical models that fit the data far better than anything we've had previously. But those theoretical models incorporate features like dark energy that we really don't understand. So we feel very uncertain at the same time as we have a very good mathematical description. This dark energy is stuff that seems to be causing the universe to expand more and more rapidly with time. It's a repulsive gravity material, exactly like the kind of repulsive gravity material that I speak about in terms of the early universe and inflation. It's very good for inflation in terms of our making the theory look convincing. First of all, it provides an example of repulsive gravity material. It's there. Right. It's not just a theoretical idea. We actually see it filling 70% of the mass density of the universe today. But in addition, it also straightens out a prediction of inflation. Inflation has from the beginning made a prediction for the total mass density of the universe. When the prediction was first made, people didn't have much of a clue, so it was as good as any number. But as the mass density of the universe was measured more and more accurately, the astronomers became convinced for a while that the mass density of the universe was only 20 or 30% of what inflation predicted. Then came along dark energy, and it made up the extra 70%, and now it's a beautiful fit. Now the mass density of the universe agrees with the predictions of inflation observationally to within a few percent. Beautiful. But this dark energy remains a tremendous mystery, theoretically. What is it? The simplest explanation is that it's the energy of empty space itself, the energy of the vacuum. That fits perfectly with everything we know. It's obviously simple, you can say it in a sentence. What's hard to believe about it is the number that this dark energy has for its total energy density. Particle physicists have no trouble with the idea that the vacuum might weigh something, might have a mass density.
And that's because of quantum mechanics. Most people would think of a vacuum that has absolutely nothing in it.
Exactly.
But in reality, because of the uncertainty principle of quantum mechanics, you have this kind of cauldron of things, particles coming in and out of existence and quickly annihilating each other.
That's exactly right. The vacuum, from the point of view of modern particle physics, is far from empty. It's a complicated, roiling sea of particles and antiparticles appearing and disappearing. So there's no reason why the energy density of that should be zero. However, if we try to estimate what it should be, we don't know how to calculate it, but if we try to estimate what it should be, we come up with numbers that are larger than this observed value by literally 120 orders of magnitude. It's the worst failure in theoretical physics since theoretical physics began.
Well, maybe the worst failure of anything numerical since numbers began.
That's probably true too. It is. So we have no understanding of where this incredibly small number comes from. We used to believe it's zero, and when we believed it was zero, we still were aware we had a problem because we didn't know why it was zero.
But something canceled out.
Yeah, zero seems like a number that you might be able to explain someday,
right.
by some simple argument that you don't understand yet. But understanding this very small number that's non-zero is much worse. And nobody really has much of a clue about how to explain it, except possibly through anthropic ideas. The idea that maybe this number varies throughout the multiverse, with different pieces of the multiverse having different values of this vacuum energy density, just randomly, different kinds of vacuum in different places, producing different kinds of vacuum energy densities. And then if you had enough different kinds of vacuum, some of them would have a very small energy density. And in fact, string theorists say they expect something like 10 to the 500th power of different vacua coming out of string theory. So if you believe that, in some places the vacuum energy would be very small. And then this anthropic argument is invoked to say that life would only form in regions where the vacuum energy is very small. And that would then explain why it is that we find ourselves in a region where the vacuum energy is far smaller than what we'd expect for the average for the multiverse. That remains highly controversial, of course. We don't know for sure that this multiverse really exists. People have a tendency to dislike anthropic arguments because we'd like to believe something more determined by the laws of physics themselves. So it remains controversial, but nonetheless, one possible explanation for this very small value of the dark energy density is the anthropic one.
In inflation, you need this stuff that is repulsive gravity. And if there is this kind of stuff in this energy of empty space, that's sort of similar kinds of things, and it certainly gives another verification of inflation. But in that process, does inflation in any way be able to explain that small number, or what other kinds of theories are there out there besides anthropic reasoning, which to some seems like giving up?
Right. Well, inflation does not explain why the vacuum energy density should be small. In fact, inflation, if you take it literally, probably suggests that the vacuum energy should be of the order of the energy of the material that drove the inflation, which is a vastly higher energy density. So inflation is no help here, I don't think. As far as other explanations, people are scratching their heads every day and have been scratching their heads ever since dark energy was discovered. And as far as I can tell, there are really no plausible explanations yet, other than the anthropic one. That doesn't necessarily mean the anthropic explanation is right. I consider the anthropic explanation to be the explanation of last resort. That is, the only thing that could convince me that it's right would be a demonstration that there's no other explanation. So far, there's no other explanation, and people have been thinking hard. So I don't really know whether it's time to tip the balance and admit that that's got to be the right explanation. But from my point of view, it's certainly a consistent explanation, and as far as I can tell, it's the only explanation we have at this time.
So, putting it all together, what is the significance of dark energy in really understanding the cosmological origins of the universe?
Well, I guess for me, the discovery of dark energy was a very sobering experience. I think before we had a clue that there was dark energy, we had the feeling for a while that the universe was going just the way we expected it to go. And we felt that some confidence that maybe it would just continue to go just the way we were expecting it to go. The predictions of inflation were being borne out very well. There was a problem with the mass density, but it wasn't that clear if the astronomers had measured it correctly. So things seemed like we really understood it. The dark energy, however, for me was a big monkey wrench. We don't have a good theoretical explanation of why the dark energy should have the magnitude that it does. It's perfectly okay for it to exist. We think we could explain that. But we're really clueless at understanding what its magnitude might be, except for this anthropic argument, which a lot of people are unsatisfied with because it doesn't seem to be based firmly on physical ideas, but instead these selection ideas associated with life.
But until one way or the other you deal with dark energy, you really don't have a final theory of cosmology.
Absolutely, that's right. I think we don't have a final theory, and I think now we feel that we're further away from having a final theory than we felt a decade ago.